Hello everybody, welcome to this second video lecture for week 1. So this lecture is just about some examples of groups, and it's a companion to section 1.1 of the lecture notes, which I hope you might get a chance to read this week. So I'm going to go through a few examples of things that are familiar to us. So unlike the first installment of stuff about the Friese groups, these are the objects that we'll talk about today are things that you all already know about. And what I'd like to highlight in this video is how much these things resemble each other in certain ways in terms of their arithmetic structures, even though they don't resemble each other at all really very much in terms of the properties of their individual elements. So we have a few slides to have a look at. I'll fill in some text here. It's all in the lecture notes for section 1.1, and indeed there are more examples there than we'll talk about in this video. So what I'm going to do now is I'm going to turn off the camera and we'll have a look at the notes. So we'll stop the video. Okay, and our first example is just a set of integers. So Z, as everybody knows, is the set of whole numbers, positive and negative and 0. It's got 0, it's got all the positive integers, 1, 2, 3, and so on. It's got all the negative integers, -1, -2. And in this presentation, here we've written Z with a plus sign after it. And that just means that the plus sign here represents the operation of addition of integers. And the observation here is that addition of integers, addition is a binary operation on the integers. And what that means is that given any pair of integers, we can always add them together and get an integer as the result. So we can add any pair of integers. And the result is always an integer. Okay, so that's saying basically the plus addition is a binary operation on the set of integers. Okay, that's fine. That's unlikely to be a surprise to anybody. We've all known that for a long time. Another observation is that if we look at the integer 0, it has a special property for addition. For addition of integers. And the special property that 0 has is that if you add it to another integer, you have no effect on that other integer, no matter what the other one is. So adding 0 to any integer has no effect. Okay, so again, that's not news, but I guess maybe it's something that we don't always focus on if we're thinking about addition. And we say that 0 is a neutral element or an identity element for addition of integers. Okay, and so neutral. I mean, I think the word identity element is more commonly used, to be honest, and it's probably what we'll use more frequently. But I like the term neutral element because the word neutral sort of captures this property of being an identity element, of having no effect when applied in a binary operation. Okay, then the final remark about this, and what we're going to do is make similar remarks about a bunch of other things that we know about that are familiar to us, and see that, you know, addition of integers is not the only operation to have these sorts of properties. So that's the first observation. We can add any pair of integers. Second one is that 0 has a special property. And the third thing is, given any integer. Okay, so here we need to kind of state a definition. Given any integer x, there is an additive inverse for x in the integers. And that additive inverse is it's negative. So for example, -4 and 4 are two integers. They're additive integers of each other. Additive inverses of each other. Okay, I haven't said what that means. And of course, you know, we sort of know that adding -4 to something is the sort of reverses the work of adding 4 to it, or that -4 and 4 are somehow opposite to each other, or that we can if we add 4 to something, we can reverse that by subtracting 4 by adding -4. What it means for two elements to be inverses of each other with respect to this addition operation is that when we add them together, 4 and -4, the result of that addition, adding -4 to 4, is the neutral element. And the advantage of describing it that way, instead of talking about subtracting, is just that it's, this notion of having an operation of some set and being able to combine two elements and get the neutral element is something that applies in lots of different situations where we might not necessarily have words like subtraction to describe what we're doing. Okay, that's our first example, and it's sort of often cited as a very nice example of a group. So we haven't defined a group yet, but I'm kind of asserting that this thing, the integers with addition, is an example of a group. Okay, our second example, here we've got C. This is the C for the set of complex numbers. We've got a little superscript on it, which is a multiplication sign. And that's it. So this thing C with this little decoration of the multiplication symbol there is the set of non-zero complex numbers. So it doesn't include 0, but it includes all the other complex numbers. And the multiplication sign here, this one, denotes multiplication of complex numbers. So we're talking about the set of non-zero complex numbers under multiplication. First observation. If we take the set of complex numbers, set of non-zero complex numbers, if we take two elements in there, if we take two non-zero complex numbers, multiply them together, we'll get a non-zero complex number as the result of that. One way to say that is that the set of non-zero complex numbers is closed under multiplication. That means if you take two elements that are there and multiply them, you still stay within this set. Second example, second observation rather, is there a complex number which is neutral with respect to the property, to the operation of multiplication? So in our last example, we were talking about addition of integers. An element of the integers that's neutral for addition is 0. Adding 0 to another integer doesn't change that integer. So here we're asking ourselves, is there a complex number with the property that multiplying it by any complex number doesn't change that complex number? And the answer, of course, is the same whether you talk about real or complex numbers or rational numbers. The number 1 has a neutral property for multiplication. Multiplying by it doesn't have an effect. So the neutral element is the complex number 1, which if you want to represent it as a kind of typical form of a complex number with a real and imaginary part, it's 1 plus 0i. Its real part is 1 and its imaginary part is 0. Okay, so slightly more complicated question is, given any element, any non-zero complex number, and let's say we call our element z, which is sort of typical for a complex number. Given any element z of complex numbers, does it have an inverse for multiplication? And does that inverse live in the same set? Okay, so in other words, given z, which is a non-zero complex number, what it would mean for it to be an inverse for multiplication would be something that would multiply by z to give the neutral element. So given some z, is there an element z dash in the same set with the property that z multiplied by z dash okay, so what's the answer? That's the question. Does every complex number apart from 0 have an inverse which is also a complex number? Okay, so the answer is yes. If z is equal to a plus bi for some real numbers a and b, not both 0, then 1 over z Actually, I'm going to write it in the next line. Then 1 over z with 1 over a plus bi, which is a minus bi. If we multiply above and below by a minus bi, the complex conjugate of the denominator here, then we get a squared plus b squared here. So this written as a complex number is a over a squared plus b squared minus b over a squared plus b squared. That's the imaginary part. And of course, if a and b are not both 0, then a squared plus b squared won't be 0. So the fractions in this description make sense. Okay, if you're in doubt about this, just try it out for your favorite particular complex number. And a question just to throw into the mix here is why, when we initially defined the set, did we leave out 0? Because 0 is a perfectly good complex number. So why are we only talking about a set of non-zero complex numbers here? Okay, that's a question for you to think about as you look at these examples and also as you read the lecture notes. Okay, our third example, this is a different one. So our example here is a gadget called GL2Q, and the operation again is denoted by multiplication. So the GL stands for general linear group. I don't expect you to be already familiar with that terminology, but that's what it is. And the cross here stands for matrix multiplication. So GL2Q, by definition, the elements of GL2Q are the set of all 2 by 2 matrices. So the 2 in GL2Q means 2 by 2, whose entries are rational numbers. So the Q, remember Q stands for rational numbers. The Q there tells us that we're talking about matrices whose entries are rational numbers. And the multiplication, and sorry, the other thing that's included in the GL part, the general linear group, is that we're talking about rational matrices whose determinant is not 0. Okay, so again, that's not, I mean, that's not supposed to be sort of immediately legible from the notation here, unless you're already familiar with the notation. Included in the definition of the general linear group is the statement that it consists of matrices whose determinant is not 0. Okay, so that's a set of objects. Again, it's closed under multiplication. Multiplication. So if A and B are 2 by 2 matrices with both of their determinants not 0, then I claim that the determinant of their product AB is not 0 either. Now certainly the product AB is going to be a 2 by 2 matrix whose entries are rational numbers because it's the product of two such things. How do we know its determinant is not 0? Well, here you might have to cast your mind back to some linear algebra and recall the very, very nice and handy fact that the determinant of the product of two matrices is the product of their determinants. So if determinant of A and determinant of B are both non-zero rational numbers, then the determinant of AB is the product of those two things and it won't be 0 either. So this is a set again, which is closed under matrix multiplication. If you take two elements that are there and multiply them together using matrix multiplication, the result of that operation will still be in that set. We're going to look at the other questions, the neutral element here, or identity element. So again, the word neutral element is a phrase that I like because I think it really captures the meaning. Identity element tends to be used more frequently. The identity element here is the matrix 1, 0, 0, 1. Okay, that's a matrix whose entries are rational numbers, 0 and 1. Its determinant is not 0, its determinant is 1, so it is an element of that set, and it has the property that multiplying any 2 by 2 matrix by this identity, either on the left or on the right, always gives us back just the matrix itself that we started with. And then the final thing is inverses. So if A is an element of this set, then the inverse of A, which is traditionally written A with a superscript of -1 in linear algebra, is of course the thing that you get if the entries of A are written A, B, C, D. Then the inverse of A is the matrix that would result from swapping the two entries on the main diagonal, switching the signs on the other two, and dividing the whole lot by 1 over the determinant. And as long as you know that that determinant is not 0, then this A inverse matrix is also an element of GL2Q. So like the other examples there that we just saw, this is an example of a set of mathematical objects equipped with a binary operation, this time it's matrix multiplication, with these properties that whenever you take two elements of the set, combine them using that operation, you're still in the set, that there's an identity element and neutral element for the operation, and that that neutral element lives within the set. And finally, that whenever you take any element of the set, it's always true that there is an element there with a property that those two multiply together or combine together to give the neutral element. And of course, the property that A and A inverse have that relates them to each other is that if we take A multiplied by A inverse, we get the 2 by 2 matrix identity. And if we take A inverse multiplied by A, we get the same thing. So again, those two elements are inverses to each other with respect to that operation. Okay. And again, bear in mind when we're thinking about this, and we will formalize all of this in the next couple of lectures, that in order to talk about two elements being inverses of each other for some operation, you need to have a neutral element for that operation. What it means is to say that when you combine those two elements under the operation, what you get is the neutral element. So in the case of integers with addition, the neutral element is 0. What it means for two things to be inverses of each other is that they add together to give 0, so they're negatives of each other. In the case of multiplication of complex numbers, what it means for two elements to be inverses of each other is that they multiply together to give 1, which is the identity element there. So they're reciprocals of each other in that sense. In this matrix example, a group or set of matrices under matrix multiplication, what it means for two elements to be inverses of each other is that they multiply together under matrix multiplication to give us the 2 by 2 identity matrix. Okay, so that's example 3. Okay, those are a few examples. And there are several more in the first section of the lecture notes, and we'll have a few more in the first round of next week's installments. So here's the second video challenge then at the end of this video. So the setup here is we've got the set S, which is the set of all matrices whose entries are integers, 2 by 2 matrices with integer entries, and whose determinant is not 0. And the problem for you to think about, basically, if you'd like to accept this challenge and send us something out, is to figure out when it happens that a matrix in this set S has the property that its inverse is also in the set S, which is exactly the type of problem we have to think about when we're thinking about group theory. Okay, that's it for the moment. See you all on Thursday and Friday. Thank you very much.